Imagine that somewhere in the world, a leader of a great nation dies, leaving the country in the hands of the second in command. Exactly when and how does that authority transfer? Do we imagine that power is a thing that can be transferred instantly, at the moment of death, regardless of whether the people involved might be separated by large distances? Or similarly, suppose one member of a married couple takes a trip to another continent, where they meet an untimely end in a tragic accident. Would we say that the surviving spouse is instantly widowed, whether they know it yet or not? I really hate both of these examples, and not just because they're macabre and awkwardly close at hand in our 2020 pandemic condition, but I bring them up because versions of these thought experiments are common when quantum entanglement is discussed by non-physicists. They're used to illustrate, supposedly, that the labeled roles and relationships that we assign through language can have a funny atemporality to them, a way of changing or participating in cause and effect processes that seem like they're outside the rules of physics that govern space and time. Within physics, quantum entanglement itself was famously described, by none other than Einstein, as spooky action at a distance. Supposedly, being widowed at a distance or having sovereign power instantly change hands across continents is similarly spooky. Except that it isn't. I mean, I will argue that the entanglement observed by physicists is genuinely spooky in a way that brings up questions about how causality works in space and time. But changes in label or status that we assign through language are not spooky, at least not in the same way. And the difference has to do with narrative, the existence or non-existence of tellable stories about what transpires. So okay, this is going to seem like a change of subject for a moment. Look at this absurdly cute puppy. His name is Sully, which is short for Sullivan, and he belongs to my friends Ash and Alex who live here at the farm. Sully was born on a different farm in central Indiana, hundreds of miles away from here, where he lived out his first few months before joining us here in Illinois. But Alex and Ash got to see lots of baby pictures, and they chose his name months before they got to adopt him. And so we might ask, thinking about action at a distance, did Sully receive his name? Did he suddenly have a name the moment it was chosen and assigned, even though he was 200 miles away? It's a less morbid reframing of the question about action at a distance and the nature of the relationships that we define through words. And I would argue that if anyone on the farm in Indiana could have studied everything possible about baby Sully on the day he was named, I don't think they would have found any meaningful correlation whatsoever between anything about his body, mind, or behavior, nor the bodies, minds, or behaviors of anyone else around him, coincident with the moment of his naming. That is, there was no direct effect across 200 miles of the act of naming. Physically speaking, the first time the naming of Sully could have mattered to Sully himself was right after this text message, in which information about the name was sent from Illinois to Indiana by an ordinary cell phone signal, nothing spooky involved. And I'll grant that philosophy provides plenty of room for viewing names and labels as having important power, or for giving human mind and language a status outside or beyond ordinary space and time and causality. I hear you, Sully. But physics is about the stuff that is within space and time, and obeys, most of the time, an ordinary logic of causality. From the standpoint of physics, there was no instantaneous action at a distance when Sully was given his name, just like there's no instantaneous action at a distance when a death causes a reassignment of labels, like head of state or widow. The change in state from unnamed to named, or from married to widowed, can't cause any effects across great distances until information is transferred, via ordinary physical means. Ordinary physical causality only allows for one event to affect another if it's possible for some kind of physical signal to transfer between them. But causality is complicated. The case of a simple, obvious chain of cause and effect, like with dominoes, where we can witness and understand every step of a sequence of events, it's the rare exception in a world in which there's so many physical processes that are unfolding simultaneously that the connections between them might be subtle. Sometimes they are partially hidden from our knowledge, or sometimes they could be interpreted in different ways depending on the context. For example, one day recently I went out in the morning and found 2 butternut squashes in the garden that had been munched by animals. Were these events part of the same story? Well, when I looked more closely, I could see that the bite marks in each case were different. So probably they were 2 separate stories. It was a random coincidence that 2 different critters attacked my squash plants in the same day. But in another sense, maybe they're part of the same story, in that it's harvest season. The squash are finally ripening, just as the trees are beginning to change color, and just as the animals in the forest are beginning to prepare for winter. Maybe it was a coincidence that 2 critters struck the squash patch on the same day, but it's not coincidence that they both did so during the fall. I got a text from the neighbors down the road last week that said, "Pumpkins are out. Prepare for swarms of invasive ladybugs." And sure enough, here they are. The species, which originated on the other side of the world, has now naturalized around the entire globe. In some places, it's even called the pumpkin ladybug, because, chased from the fields by the plows, they try to invade human houses every fall right around harvest time. Pumpkins don't cause ladybugs, and ladybugs don't cause pumpkins, but their appearance is related by the harvest process in general, as part of a bigger cause and effect story of seasonal change. And also as part of an even bigger cause and effect story that has to do with how land use in North America has changed over time, about migrations and colonizations by humans and plants and insects all interacting with one another. These broader causal stories are much harder to describe in terms of simple sequences of events. Most real events are not like falling dominoes. How we describe the causal story may depend on what we view to be important. Is the important set of causes just the change in seasons, or is it something about industrialized agriculture? Is the important context the local context or the global context? Without any kind of spooky action at a distance, the explanatory causal stories that we can tell often link the present and the past, or link events in the here and now to events in other times and in distant places, simply because few events have a simple, single, domino-like trigger. Sometimes the word entanglement is used to describe the muddled and context-dependent storytelling that's necessary for complex macroscopic causal stories. But I still want to argue that the type of entanglement studied by physics is different, and the reason has to do with the way that it implies a type of causation that seems to defy any story whatsoever. Quantum entanglement rightly gets the reputation for being spooky because it combines the physical phenomena of randomness, complementarity, conservation laws, and spatial separation. So let me start with a comment about randomness. People think that when something is random, it means we don't know anything about how it works or what it will do. But in a way, it's actually exactly the opposite. Knowing something is random means we know quite a lot about it. I mean, for example, knowing that there's some randomness to the way that the leaves fall in the yard means I know that this is the kind of thing I expect to happen naturally, and not this. Therefore, if I see a pile of leaves in the yard, it's a type of pattern that requires some kind of extra explanation. It speaks to the presence of a specific, non-random cause. Games like Yahtzee work on the basis of random chance being actually quite predictable. Otherwise, the games wouldn't be fun or fair. I asked my kid and her friend to sit with me on the porch for a while and roll dice, with a wooden barrier between them so that the dice could not affect one another and each kid couldn't see what the other rolled. Imagine you're one of these kids. What would you observe? Well, most of us have rolled a 6-sided die before. We know that you get a random pattern of numbers. If you do it enough times, you should roll a 2 about the same number of times as you roll a 4, and so on. Likewise, if the two kids both recorded their dice rolls and compared their data later, we would expect them occasionally to see the same thing, to see apparent coincidences, like this time that they both rolled a 4. But a little math could easily tell us if the rate of those coincidences was consistent with random chance or not. Again, because true randomness is very predictable. Here's a variation on a similar scenario. This time, I'm shaking up 2 Yahtzee tokens, one red and one yellow. I shake up the tokens so that they land randomly. Whichever one falls to the left, I give it to the kid on the left, and vice versa for the kid on the right. Assume that I don't tell the kids anything about my methodology, but ask them to keep track of the color of the token that they receive each time. Over time, they could both figure out that the pattern they got was consistent with a random 50% chance of getting yellow or red. But this time, if they compare their notes later, they will find a completely perfect correlation. Every time one kid got yellow, the other got red, and vice versa. What does this show? It shows that the tokens received by the kids may be random, but they're not independently random. If the kids compared notes, they could infer that the tokens they received were prepared jointly, with the constraint that the 2 colors would always be different. And if they know that the tokens they receive are not independently random, it gives each child a funny way of knowing something about what the other will see. And that would be true even if the kids were separated by hundreds or thousands of miles instead of just a couple feet. If one kid opens her hand and sees yellow, she instantly knows that the other kid will see red. The link or constraint that I imposed here was that I ensured that every time I had only one red and one yellow token in my Yahtzee cup. The colors were constrained to always be different, even as they randomly varied for each kid. In physics, the most important constraints that can link random events are the constraints imposed by conservation laws, like the conservation of momentum, angular momentum, and energy, which I discussed a bit in the last video. And as a reminder of what I mean by a conserved quantity, it's an empirically determined way that measurable features of an isolated physical system will always stay the same, despite whatever changes, random or otherwise, occur within that system. To Lucille the chicken, there's a conservation law governing the level of water in her drinking station. The system is set up with an automatic valve so that every time a chicken takes a drink, the water is automatically replenished to the same level. To Lucille, this is a structural feature of her reality that never changes. Of course, here, That structural constraint is handed down from on high, imposed by the design of the watering system and the fact that we're consistent about keeping the bucket filled. I mean, we have to be, otherwise we would have some very grouchy, thirsty chickens. I don't like to think of the conservation laws in physics as prescripts that are somehow handed down from on high. Instead, I like to think of them as a reflection of the intrinsic structure of space and time. They're a type of structural sameness through change. And those structural constraints can translate to relationships between random variables, like the properties of quanta. As a simple example of what I mean, think back to the generic experimental setup that I described in a previous video. We have a source on the left that produces a beam of electrons. We shoot those electrons across an empty space and then detect them with a sensor, a camera, or a screen on the right, which records a dot or flash each time an electron strikes. The pattern that we see over time shows both the intrinsic random nature of the position of the electrons, but also at the same time shows the influence of the constraints imposed by conservation of energy and momentum. All the electrons end up in a relatively concentrated area of the sensor system. They don't end up way off the screen to the left somewhere, for example, which would violate the conservation laws in play for an isolated system like this one. It's really just like the way that the leaves in my yard fall randomly on the lawn, but they only fall down and not up. They're constrained by the underlying laws of physics and the presence of gravity, even if they're random. Okay, so far I've argued that the presence of structural constraints on a physical system, combined with the presence of randomly varying properties, can set up a situation in which the properties of quanta can vary randomly but have correlations among them. It's very similar to this whole situation. And just like in this situation, the presence of the constraint, if you know about it, means that doing a measurement on a part of the system lets you make inferences about measurements that might take place on other parts of the system, even at a distance. And so far, I haven't talked at all about any kind of spooky action at a distance, because really none of this is spooky yet. The spooky happens, and it does happen, on a quantum scale, because not only are the configurational properties of quanta capable of behaving randomly, but they also exhibit complementarity, which is also sometimes described through an idea called the uncertainty principle. And in the previous video, I discussed this idea through a personal metaphor involving yarn crafts and my own sense of gender identity, both of which I tend to prefer to be a little bit non-committal about. But the metaphors don't capture what is really happening for quanta with their complementary properties. So here's where I'm going to stop talking in metaphors for a bit and talk about the real thing, using electron spin as an example. Microscopically, a single electron has a property called spin that makes it act like a tiny magnet with a north pole and a south pole. Even though the pictures are not to be taken literally, the spin does have an orientation in space, and we can use an arrow to indicate that idea. That means that individual electrons can be pushed and pulled by other magnets, depending on their orientation. If the spin of an electron is oriented so that its north pole faces the north pole of a magnet, it will be repelled. Or if it faces the south pole of a magnet, it will be attracted. The fact that electrons are little magnets means that if I stick a magnet above a beam of electrons with randomly oriented spins, it will affect where they land. The electrons' paths will be deflected, a little bit either towards or away from the magnet. And in fact, this kind of experiment is a way of measuring the spin orientation of the electrons relative to the vertical direction. Similarly, this kind of situation is a way of measuring the orientation of the electron spin relative to the horizontal direction. The weird thing is that the properties of the electron spin orientation, as measured in two perpendicular directions, are complementary. And I can't really draw anything to tell you what I mean by that, or give you a good macroscopic analogy, because this is the thing about quantum properties that fundamentally doesn't have any macroscopic analogy. For a single electron, we find that how it will respond to this kind of geometry, and how it responds to this type of geometry, are types of knowledge that are radically incompatible with each other. And hopefully you'll forgive me for how crappy these graphics are. But the point is that physicists have done experiments with electron spin in which they subject electrons to a series of magnets that are oriented in different ways. And what they find is that if you measure the spin in one direction, say the vertical or z direction, this changes. In fact, it randomizes what the spins will be if we measure them with a magnet oriented horizontally. And then measuring the spin horizontally, this changes. In fact, it randomizes what the spin will be when we measure it again vertically. Schematically, we might summarize this kind of experiment like this. We start with a bunch of electrons with random spin orientation, what we would call an unpolarized set of electrons. And let's say we have 1,000 of them. We subject them to a vertical magnet, and that separates them into two groups. One of the groups is attracted, and the other group is repelled, half in each group. Now we subject those to a test of how they respond to the magnet oriented horizontally, and each batch splits into two again. But then imagine that we take these 4 batches of electrons and subject them to another vertically oriented magnet. If the first measurement that we made using a vertical magnet actually measured a permanent fixed property of each electron, then this is the kind of thing that we would expect. We would expect that since we already sorted them into categories based on how they respond to a vertical magnet, we should just be checking those categories, and yeah, they're still there. But that's not how it works in quantum physics. What we actually find when we apply another vertical magnet is that every single group ends up splitting in half again, half showing they're attracted to the magnet and half repelled. It's as if the fact that we measured their response to the horizontal magnet totally erased any information about how the electrons would respond to a vertical magnet. And that truly is the essence of complementarity. A measurement of the spin in one direction destroys any information about the spin in the other, perpendicular direction, and vice versa. And just as a footnote, if you want to read more about the scenario that I just described, it's got a name. It's called the Sequential Stern-Gerlach experiment. But anyway, the upshot is that the manifestation of complementary properties like this on the quantum scale leads to the description of those quantum properties as indeterminate, that is, lacking any clear and definite existence prior to measurement. In my own personal vocabulary, it leads to the non-narrative nature of quantum physics. Prior to measuring an electron spin, there simply isn't a story you can tell about how that spin is oriented in space. This is true because your choice of how to measure the spin will radically change what kind of story is even consistent with the results of the observation. And it's really the presence of complementarity, the strangeness of complementarity, combined with conservation laws, that makes quantum entanglement truly much stranger than anything I can do with dice or Yahtzee tokens. Suppose that I start out with a pair of electrons that have opposing spins. Their spins cancel out. Because spin is conserved in an isolated system, the spins should always cancel out as long as we maintain the isolation. But because spin isn't a fixed, determinate property, every time we measure the pair, they could be canceling out in a different direction. They could be like this, or they could be like this instead, or like this. Our pair of electrons has a real relationship between their spins, but the specific orientation of those spins lacks the same kind of reality. So now imagine that instead of giving each kid a red or yellow token, I gave them one of my two electrons with the linked spin. Just like in the token case, if one kid makes a measurement with a magnet and finds that the spin of their electron is pointed in a given direction, the spin the other kid will find must be perfectly opposite. Only, unlike in the Yahtzee token case, we can't think of the electrons as having had that same spin all along. And the relationship of complementarity between electron spins measured in two perpendicular directions means that one kid's choice of how to measure the spin on her side of the barrier actualizes certain possibilities for the spin orientation on the other side of the barrier, while totally randomizing others. This is kind of a spooky action at a distance. To maintain the conservation relationship, the spins always have to oppose each other. But because of complementarity, the way that one kid chooses to measure her electron affects the properties that are possibly real for that electron, and thus somehow seems to affect what properties are possibly real for the other one, instantaneously. If next time she chooses a different orientation to measure the spins, that too will change what has to happen on the other side of the barrier for her friend. And later when the kids compare notes on what happened, they'll see that the results show perfect correlations between spins, no matter what choices each kid made about which spin direction to measure and which to effectively scramble through complementarity. And this happens even if we separate them by a large distance. I mean, even on the other side of the globe. And this is a different kind of situation than the situation with the supposedly instantaneous widowing or naming or whatever. In those cases, if we compare notes from every measurement that could be made in two distant locations, nothing could have actually physically changed at the same time in both cases, without the ability for information to travel from one to the other. But quantum entanglement can show correlations among distant events that go beyond what we would expect for pure random chance, even random chance with a common constraint. Because of quantum complementarity, there's a deeply untellable story about the properties of quanta prior to measurement, and the agency of the measuring apparatus in manifesting reality means that a choice made on one side of the globe can somehow affect what could possibly happen on the other, if we're dealing with true quantum entanglement anyway. Quantum entanglement seems to imply that the universe has, in it, a type of causal influence across a distance that simply doesn't have a macroscopic analog. And even though it's been many decades since Einstein called it spooky action at a distance, the spookiness is not something that physicists have either explained or resolved. But I really do want to emphasize that quantum entanglement requires a special set of conditions. We need to be dealing with a well-isolated system in which we can be sure that a conservation rule applies. And the true spooky aspect of entanglement isn't apparent unless we're also working with complementary properties. In practice, creating and maintaining entangled pairs of electrons or photons or anything else, it's extremely hard to do because quanta are so tiny, and any interaction they have with their surroundings will muddle the integrity of the system. We can't really just put quanta in a box and think of them as isolated. We have to work really hard to create that isolation. And for exactly that reason, it's exceptionally difficult to imagine that quantum entanglement could create meaningful linkages between the thoughts or behaviors of one organism and another, or meaningful links between events on one side of the planet and events on another continent. But for some reason, a lot of people desperately want quantum entanglement to provide exactly that kind of loophole in our ordinary experience of causality. And I'm sorry to say that it just doesn't. Quantum entanglement is an oddity that does make us question how causality works in space and time in fundamental physics. But it's not a way to evade the ordinary macroscopic rules of causality and how things work. And personally, I'm fine with that. I mean, reality on the macroscopic scale is complex and weird enough already. We don't need to add any extra spooky.